right. Well, we have heard a lot about splines and about the B-splines, orthogonalization of splines. And we have also heard about functional data analysis, integration of B-spline with functional data analysis. And we also heard about survival analysis and approximation using polynomial and the splines. Okay, you want something different? This is different, very different. I think it's time to talk about data collection. Experiment design is about data collection. The talk is based on some of my recent works, and so that I will make the expository and a little bit broader. Yeah. The title is Fractional Factorial Design under Baseline Parametrization. And baseline parameterization is relatively recent development. Along the way, I will talk about a little bit about the common orthogonal parameterization. This is the outline of the talk, and I will give a brief introduction to two-level fractional factorial designs. And then I will speak of factorial effects, one set of factorial effects under orthogonal parameterization, the other under baseline parameterization. And then I talk about designs, that is, how we are going to collect data for estimating baseline main effects. And then briefly talk about further topics. Two-level factorial experiments. In scientific technology investigation, we need to collect data. We rely on experiments. Broadly speaking, there are two types of experiments. One type is comparative experiments, where you want to compare several treatments. And the other type is factorial experiments, in which what we want is to study the effects, several factors on the response variable. Comparative experiments, and here the goal is to compare different treatments. Examples can be two different fertilizers. You want to compare different fertilizers and to see whether they have they make difference in enhancing the yield tomatoes. Another example is the let's say there's 3 drugs for lowering blood pressure. The general approach in the data analysis is to conduct overall F-test to see whether there's any difference in the treatments. If we want a more detailed comparison, we can use the treatment contrasts. If you want to measure a certain type of difference, you can use this contrast. If you want a difference in that direction, you can use another contrast. Okay, as we all know, randomization is crucial in such type of analysis. And basically, although I talk about F-test, the theory behind it, the foundation is randomization. Provided we randomize, then the F-test is okay. If you don't randomize, there's no guarantee. So generally, we can say that randomization not only help us eliminate systematic variation in the experimental material, also help validate model assumptions, the standard model assumptions. And because of this, such design are called complete randomized design. Complete randomized design means that you want to assign the treatment randomly to the experimental units. In order to collect data, we need to apply the treatments to these units. When you observe response variable, the response depends on the particular treatment and also depends on the experimental unit. The difference in the experimental units can be regarded as noise. The difference in the treatments are the signal. All right, but because it's different in the experimental units, and the noise come in the difference in the treatment. So one idea to deal with the difference in the experiment is use this idea of blocking. The blocking idea is such that we just divide, when the knowledge available, divide the experiment units into groups. The groups are called blocks, such that the units within each block are relatively homogeneous. And this way, we can apply all the treatment to a block because these units are relatively same or similar, then the signal can stand out. In the perfect scenario, you have blocks so that all the treatment can be applied that give you so-called randomized block design. Or you can say completely randomized design. I mean, complete randomized block design. Very often, it's hard to create blocks that are large enough to accommodate all the treatments. In this case, we have to use so-called balanced incomplete block designs. And sometimes we have knowledge to block experiment units in two directions, then one can use Latin squared designs. And if you want to block experimental units in three directions, then we can use Greco Latin squares. And you can do even more using sets of orthogonal Latin square, more generally using orthogonal arrays. Now come to factorial experiments. In factorial experiments, the goal is to study several factors to see whether they have any effect on the response variable. Especially in inductive experiments, where a large number of factors are studied. The goal is to identify the active factors or important factors. In this case, two levels are generally taken. It's sufficient to identify important factor. Once the important factor identified, you want detailed study, then you can choose more levels. Okay. And when you have several factors, each factor have several levels, and every level combination can be regarded as a treatment. Right? And we want to choose the treatment contrast so that they represent various meaningful factorial effects, right? In this talk, I will focus on two-level factorial designs. As I mentioned earlier, there's two ways to choose factorial effects. One is using orthogonal parametrization. The other is use baseline parametrization. I will provide two simple examples to explain both. In the first example, this is an example from chemical reaction example. And the response variable is the yield certain chemical compound. And this experiment, three factors are studied. First factor is temperature. Two levels are used, 100 degrees Celsius. The other level, 300 degrees Celsius. Second factor, concentration of some sort of solution. 1%, one level, the other level 2%, and the chemists use the catalyst A and B, two levels. In this case, in this example, we have no preference of either of the two levels, but the two levels are symmetrical. And you see that the two levels are equally important. Now let's look at another example. This is a marketing example. The response variable represents the yield of a certain product. And a supermarket want to conduct this experiment to see whether making some change can affect the yield of certain product. 4 factors are studied. One is shelf space. You go to supermarket, you find something, they will have some product have this shelf space, and others have a lot of shelf space, all right? It's a two-level study for shelf space, normal shelf space, and the other level is try to double the shelf space. And initially, maybe this much, and then you want to try to see whether I devote more shelf space to this product, whether it can make difference, right? So double the shelf space. And second factor, promotion. Promotion means you put a sign, at the entrance of the store or center of the flyers. And no promotion is level 1. Yes, promotion is level 2. Third factor, location quality. In the stores, different locations are different. And some locations are better. Some locations are called the prime location. Okay? The prime location are those at entrance, at the cashier, the exit, and those near milk, for example, the beer, those are good locations. There's a standard location, prime location. First factor, price. Okay? Normal price, we certainly know that if you reduce price, it can make difference. So let's see whether 10% off make difference. And in this example, the two levels are asymmetrical, not symmetrical, different. There's one level we prefer to use, right? Like certainly for the shelf space, the normal shelf space preferred. You don't want to use actual space if it doesn't make difference. Promotion, no promotion, you don't need to spend any money, right? You don't do anything. If you do promotion, in some work. Location quality, the prime location are good one. So in this case, we would prefer the normal shelf space, no promotion, standard location quality, normal price. And so these are preferred levels or called default level. The other level are test level. In this case, you see that the two levels are different. You have one preferred level and the other, it costs money. Factorial effect. As I said, we can define factorial effects using either orthogonal parameterization or baseline parameterization. Orthogonal parameterization reaches property when the two levels are symmetrical. And it produces sets of orthogonal contrasts. And if you read any standard textbook, you will see that this is all these theory, standard theory factorial design based on orthogonal parameterization. Baseline parameterization is useful when two levels are asymmetrical, and it gives sets of factorial effects. Yes, these are contrasts, but the contrasts are not orthogonal. That makes the theory a little bit difficult to develop. This is relatively recent development in the theory factorial design. And I will use this chemical reaction example to illustrate orthogonal parameterization. This simpler one, I only use two factors. Chemical reaction example, only use the temperature, one factor, concentration, the other factor. Simpler example. Temperature has two levels, concentration two levels, where these four mu's, mu1, mu2, mu3, mu4 are the mean response for the four level combinations, right? Then orthogonal parameterization of the factorial effects are defined as follows. If you look at beta 1, is the average mu3, mu4 minus average mu1, mu2. The average mu3, mu4 anyway, my hand. mu3, mu4 correspond to temperature at 300 degrees, right? mu1, mu2 correspond to temperature 200 degrees. So if you take average mu3, mu4 minus average mu1, mu2, that's the mean response increase when you change the temperature from 200 to 300 degrees, right? Therefore, it's called main effect of the temperature. Similarly, the average mu2 and mu4 minus average mu1 and mu3, this is the mean response increase when you change concentration from 1% to 2%. It's called main effect of concentration. And everything left is called interaction effect. All right? Now, the marking example, this is also simplified, only two factors. There's promotion and the price. mu1, mu2, mu3, mu4 are also the mean response. And the baseline parameterization define factor this way. All right, you hold the other factor at the baseline level. Then you change the level of one factor while holding the other factor at baseline level. See what's the difference. All right, look at the mu3 minus mu1. Mu3 minus mu1 is when you change promotion from not promotion to yes promotion while holding price at normal level, right? So you don't change the price, just change the promotion from one level to the other. This is the effect of promotion. Why? Because we prefer the default level. Okay? Similarly, we can define the main effect of price. And this is defined as the change in the mean response while holding the other, which is promotion at default level. Okay, interaction also represent everything left, right? That is the response that cannot be explained by the main effect only. Okay, in general, you can define the factorial effect under orthogonal parameterization by using this expansion. So the mu's, here x's are the factors. It have two levels, +1 and -1, the two levels. And those coefficient beta are the factorial effects under orthogonal parameterization. This is implicitly defined. One can actually solve this to obtain the beta in terms of the mu's. Right? And the baseline parameterization, it can be defined this way. You just choose the two level, the factor at level 0 and 1, rather than +1, -1. Then you got these thetas. These are the factorial effects under baseline parameterization. All right, next come to the design part. And the scenario I'm considering are screening experiments. where we want to study larger number of factors. The goal is to identify important factors. Identify important factors. Once important factor identified, if you want to continue and do more detailed study, you can choose more levels. Use 2 levels, and the goal is to estimate the main effects. All right. And it will be ideal if you want to use, if we can use full factorial design, meaning that all level combinations are used in your design. But when the number factor is large, even moderately large, and the total number combination is astronomical, right? And for example, for 10 factors, the total number combination 1024. Number factor 20, you got over a million in number combinations. And because of this, fractional factorial design helpful. So consider fractional factorial design for estimating the baseline May effect. And here I give you one example of a design for estimating baseline May effects. And it's given by this matrix where each row represents one experiment or one level combination, and each factor represents one factor. So this is a design of 4 runs or 4 experiments for 3 factors. So basically, if you look first row, meaning that for all the 3 factors, you set their levels at default level for the first experiment. Second experiment, first factor, you set at default level. Second factor at the test level, third factor, test level. And that's 4 experiments. This is a fractional factorial design because for 3 factor, total number combinations is 8, right? So this is only a fraction of 8. So it's fractional factorial design. Now let's consider the model. The full model under the design is given by this, in which theta 0 represents the intercept. Theta 1 is the vector of all main effects. Theta 2 is vector of 2 factor interactions, and so on. And this is one vector is the vector of 1s. It's the model matrix in your linear model, the column of O1s. Z1 is the corresponding model matrix for main effects. Z2 is corresponding model matrix for the 2 factor interactions. For design people, we prefer all these model matrices rather than design matrix. Design matrix is design. Depending on different model you're fitting, and you have different things. And this epsilon represents the uncorrelated random error at 0 mean constant variance. Okay, this is the full model, but our interest lies in estimating the main effects. Main effects, theta 1, under possible existence of 2 factor interaction, 3 factor interaction, and other interactions. Okay. Now, consider the main effect model. Main effect model contains intercept plus main effect, right? So it's basically first 2 terms. And write that model, main effect model in matrix form. All right. Then you obtain least square estimator from fitting this main effect model. And then we know that the standard linear model theory, the various covariance matrix of this data parameter, which contain intercept and the main effect, is given by that. All right, but we fit the main effect model. The true model actually is the full model. Under the true model, the least square estimator is bias. Okay? You calculate the bias will has theta2 in it, has 3 in it. So the first term has theta2 in it, is the contribution of the bias due to two-phase interaction. The next term has theta3 in it, is the bias due to three-factor interaction. If the mean effect model is correct, then there's no bias, right? So my theta there include intercept and the main effect, but what we are concerned about are the main effects. So you got the variance covariance matrix of the intercept and main effect is like this, but we only concerned with the main effect. So we can just take this submatrix, the first row and the first column and the first row. You get the variance covariance matrix of the main effects estimators. All right, the bias actually is a vector, right? The bias on the intercept, bias on the main effect. If you remove the first entry, you get the bias vector on the main effects. All right. So basically, we can obtain the variance covariance matrix of the main effect and the bias vector for the main effects. Okay, now design. So we certainly like to have a design that give us small variance and also small bias, right? We consider three approaches. One is to use orthogonal arrays. The second class design are so-called one factor at a time design. And third class, compromise designs. And we'll discuss all of them one at a time. This is what orthogonal array can help us. If this design Z is orthogonal array of strength 2, just orthogonal array, PB simple, then it minimizes the variance covariance matrix. That I won't go into detail. You don't really minimize the variance of the matrix. You might minimize certain aspects of variance covariance matrix. But for now, let's just say that if the design is orthogonal array, it minimizes the variance. Okay? So we got the variance minimized. And next, there are lots of orthogonal arrays. So after variance is minimized among all the orthogonal arrays, then I can select one that minimizes the bias. How do I do that? I will first minimize the bias due to two-phase interactions, theta2. Then I will minimize the bias due to three-phase interaction. This is called the minimum aberration criteria. So we minimize the variance first, and then minimize the bias due to two-phase interaction, and then due to three-phase interaction. Why you want to do it sequentially? Because generally, we believe that the main effect more important than two-phase interaction, two-phase interaction more important than three-phase interactions, and so on. So you want to concentrate your effort on minimizing the bias due to two-phase interaction first, then three-phase interaction. Okay. I'll give you some example of orthogonal arrays for those who never heard about orthogonal arrays. Okay, first design has four runs and three factors. It is orthogonal array because if you look at any two columns, I don't know whether you can just look at the first two columns. First two columns, and then you see, look at the rows, you see 0, 0, 0, 1, 1, 0, 1, 1, right? Two levels. These are all the four combinations. Each of them occur exactly 1, which is true for any other two columns. If you look at second and third column, you see same property. You look at the first and third column, you also see same problem. Okay. The second design, A runs 5 factors. They also have similar property. If you look at any 2 columns, this time you also see all 4 level combinations, 0, 0, 0, 1, 1, 0, 1, 1, but each of them occur exactly twice. So orthogonal array probably basically say that if you look at any 2 columns, each of the 4 pairs occur exactly same number of times. That's orthogonal array. You want your design like this, then you minimize the error. Briefly talk about orthogonal constructions. Those who have taken experiment design course or have exposure to experiment design, the standard textbook, it generates fractional factorial design by using the interaction columns. Those fractional factorial design are called regular fractional factorial designs. Can be constructed for run sizes that are part of 2, right? And these designs are good, has limitations, right? Because the gap in the run size is getting bigger and bigger. So if you can afford, for example, 20 experiments, then 16, you can use 16, save for runs. But if you want to use, you really want to have at least 20 runs, the next one is 32. However, if you use the so-called non-regular fractional design, then you can have run sizes that are multiple 4, which are much more flexible. And these can be obtained by using Hadamard matrices. Hadamard matrices exist. It's not quite sufficient, but necessary, but close to sufficient. Basically, I can tell you that orthogonal array, for all practical purposes, can be constructed for every run size that is multiple 4. For example, 20, you can obtain orthogonal array. 12, you can obtain orthogonal array. 28, you can obtain orthogonal array. If you insist using regular fractional factorial design, you don't have design 12 runs, you don't have design 20 runs, you don't have to have design 28 runs, and so on. Okay. Now, starting with orthogonal array, one can obtain many other orthogonal arrays by doing isomorphic operations. What are isomorphic operations? For orthogonal array matrix, if you permute the columns, it's still orthogonal. If you permute the rows, it's still orthogonal. If you switch the 2 levels, 0 to 1 switch, it's still orthogonal array. So starting from 1 orthogonal, you can obtain a very rich class of orthogonal array. Under orthogonal parametrization, all these isomorphic operations give you essentially same design. But under baseline parametrization, yes, row permutation does not really change the design. Column permutation does not really change the design. But if you switch the 2 levels, you got the different design. Okay? And that's why one reason baseline parameterization problem much more difficult. Okay, next cloud design, 1 factor at time design. And I'll give you example later. So 1 factor at time design, the nice thing about it, it has 0 bias, no bias, 0. So this is true only under baseline parameterization. And since they have no bias, and 1 factor time design, you can do further design selection by minimizing the variance. So this approach, you minimize the bias first, and then minimize the variance. in the orthogonal approach, you minimize variance first, and then you minimize the bias. Okay? These are examples of one factor at a time design. One factor time design only use the runs of all zeros. That is all use the baseline levels, and you only allow one factor at the test level, all the other at baseline level. So if you look at these design, they only contain these runs: 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. Only one factor has test level 1. All the other are 0. Okay? If you use design like this, these are one factor at time design. And they have 0 bias, no bias. Well, I guess if you the first part, you minimize variance first, then you minimize bias. The second part, you minimize the bias first, and then you minimize variance. And why don't we minimize simultaneously? Well, certainly this is hard to do, but can be somehow done. And you want to consider compromise design. Take some balance consideration, the bias and the variance. One can obtain such a design by modifying the OFAD design, or modifying orthogonal or combine the two cluster design in some ways. There are further topics. And the first one is multivariate. One can obtain the relationship between the two parameterizations. That is the betas and the thetas. Beta are the factorial effect under orthogonal parameterization. The thetas are factorial effects under baseline parameterization. The relationship, very clean one, can be derived. And it has some consequence in terms of designs. For example, one can consider design for echelon models. These are models more general than effect models. Basically, if your model contains a two-factor action, and then the two main factors should be equal. That makes sense, right? Anyway, the theory and the result can be generalized to echelon models. Recently, we also did some work on mixed parameterization. One can argue that why all the factors need to be baseline level, baseline parameterization. So either or approach, obviously, it's not reasonable. In practice, some factors may have a baseline levels. The other factors, the two levels are symmetrical. So in this case, you allow some factors, the two levels are asymmetrical, other factors are symmetrical. That's our recent work. And these are some references. The first group of references are give you some the scenarios. Baseline parameterization is important. And the next group of references discuss fractional factorial design under baseline parameterizations. The last group of references are some generalizations. People have done work on baseline parameterization from more than 2 levels. That's all I have. Thank you for your attention.